Resonance is hugely important in organic chemistry. In this course, we'll explore resonance way beyond what you have seen in general chemistry. This video will be a refresher of what you might have learned so far, as well as a preview of what we'll be talking about in this course. In the Lewis structure video, we drew the structure of formate HCO2-. It looked like this, and here we'll show the formal charge on one of the oxygens as we talked about in the formal charge video. However, we could have equally drawn another structure with a double bond between the carbon and the other oxygen. Which structure is correct? Both and neither. These Lewis structures are two valid structures that keep the same connectivity of the atoms. The H, C, O1, and O2 are in the same place. Only the double bond and the lone pair moved. When the connectivity of a structure stays the same, but bonds and/or electrons move one place, the two structures are called resonance structures. A double-headed arrow is used to show that these two structures are representations of the same molecule. In reality, neither of these structures represent the molecule accurately. Measurements show that both of these CO bonds are the same length, between the length of a single bond and a double bond, and both oxygens have a partial negative charge. We can draw a picture that is more representative of reality like this. These dashed bonds show that each CO is more like 1.5 bonds, and this little symbol, a delta, shows that this atom has a partial negative charge instead of a full negative charge. It would be confusing to draw the lone pair electrons, so I left those out in the structure. Now, let's look at this example again, considering the hybridization of the atoms. We can tell that the C and the first O in the first structure are sp2 hybridized because of the presence of a pi bond. We might think that this second O is sp3 hybridized because it has 4 separate electron domains and no pi bonds. However, when we look at the second resonance structure, now the second O is sp2 hybridized. When we draw resonance structures, the connectivity of the atoms cannot change. Remember, we kept the H, C, and each of the O's in the same place when we drew the second structure. However, the hybridization of an atom also cannot change. It turns out that all 3 atoms are sp2 hybridized, and this gives the compound a special stability. If 3 or more p orbitals on neighboring atoms are aligned, the electrons will be delocalized. That means that the electrons can spread out and be shared across the 3 atoms, rather than being trapped in a single pi bond or lone pair orbital. Another common example of resonance is with benzene. You've probably seen benzene before. It has alternating single and double bonds around the ring. We can draw a resonance structure that looks like this. The location of the single and double bonds are switched. However, in reality, all 6 pi electrons are delocalized across all 6 bonds because we have 6 p orbitals that are neighboring around the ring. This gives benzene a very special stability that you will hear more about in later chapters. The more neighboring p orbitals that we have aligned, the more stability the compound gains in general. We can draw a resonance hybrid for benzene like this. Now, let's take a trickier example for our last one. Here's the structure of formamide. If we draw it like this, there are no formal charges, so this is clearly the best Lewis structure. However, the bond angles around this nitrogen are 120 degrees. This experimental information tells us that, surprisingly, the nitrogen is sp2 hybridized. We can draw a resonance structure for formamide that looks like this. We would call this resonance structure a minor contributor because it has formal charges, so we know the molecule looks more like the first structure I drew. We would call that structure the major contributor. However, the lone pair and the double bond are conjugated, and the N, C, and O are all sp2 hybridized, as this increases the stability of the compound.